Welcome back. In this video, we're now prepared to apply the chain rule to some computational problems. So suppose that z is a function of x and y, such that f of xy equals x times sine of y, and we're told that x is equal to t squared and y is equal to 2t plus 1. Let z equal g of t. So at the end of the day, z is ultimately a function of t. Compute g prime of t directly and by using the chain rule. So here, let's just off the side draw our diagram, and we know that z depends on two inputs, x and y, each of which depend on this other variable called t. So we know we have a chain rule problem because we see that there's a chain of relationships going on here. Z depends on two variables, both of which depend on another variable. And so, once again, we can label these and call this dz dx and dz dy. And then we know that x is a function of t, so we'll have dx dt and dy dt. So once again, we're using the partial operator here because z is a dependent variable that has two independent variables, but x and y can be thought of as dependent variables that only have one independent variable, t, and so we don't need to use the partial notation here. So to compute this using the chain rule, we would, as usual, perform our, we want to compute dz dt, and we're going to write the calc 1 notation for that because t is ultimately just one variable that z depends on down at the bottom line. And so this is going to be the product of dz dx and dx dt. Okay, so that's the product of what we have going down this chain in this direction. And then we're going to have also the chain going down the dependency on y. So dz dy times dy dt. So in order to get that, we need to, and that's the same thing as g prime of t, right? So g prime of t, another way of writing that is dz dt. We're writing z as g of t, so we could also reference z by the name that it's given. So to find these four, or to compute dz dt, we would need the four components. So we need to compute the partial of z with respect to x, and so that's going to be of this original function here. Dz dx is going to be the derivative of this guy with respect to x. That is going to come out to be sine of y. So we treat y as a constant, so you could factor out the sine of y, and the derivative of x is 1. Dx dt is going to be the derivative of x equals t squared, and the derivative of t squared is 2t with respect to t. Now we have to compute the other two partials, dz dy, and dz dy is going to be the derivative of x times sine of y. X is a constant. The derivative of sine of y is cosine of y, so we'll have x cosine y as our partial. And the derivative of y with respect to t, y is given to us with respect to t as being 2t plus 1, and the derivative of 2t plus 1 is simply 2. So we need to now compile all of these, and we are going to come up with dz dt equals dz dx, which is sine of y, times dx dt, which is 2t, plus dz dy, which is x cosine y, times dy dt, which is 2, so I'm going to write that as 2x cosine y. We could rearrange terms, we could reverse the order of multiplication, but ultimately this would be our answer if we were to compute it by using the chain rule. Now it says also to compute this directly, and directly would mean that what we're trying to do is express z as a function of t. In order to do that, we know that x is equal to t squared, so we can substitute x with t squared, and we know y is equal to 2t plus 1, so we can substitute y with 2t plus 1. So let's go ahead and do that. What we're going to get, and I'm going to do this off to the side here, so this is going to be directly. Okay, so because I know z is equal to x times sine of y, and I know that x is equal to t squared, y is equal to 2t plus 1, I can make my substitutions in here and write this as z is equal to, I'm going to replace x with what x is, and x is t squared. Replace y with what y is, and y is going to be 2t plus 1. So now I've written z explicitly in terms of t. So you've heard me say, well, z ultimately depends on t, and if I make a couple of substitutions, I can eliminate x and y from that equation. So to compute the derivative of this, I see that I have, this is a Calc 1 problem now. We have one variable, and since it's a product of two functions of t, I have to use the product rule. And so let f equal t squared, let g equal 2t plus 1. Therefore, f prime is 2t, and g prime is 2. All right, so now if I write the product rule, which says that the derivative of z with respect to t is going to be f prime g plus f g prime, and I make my substitutions in here. I have 2t multiplied by g, which is 2t plus 1. And I can also write f g prime as t squared times 2. And it is actually now evident that we have forgotten to write sine of 2t plus 1 over here. So let's retract our statement and rewrite g as sine of 2t plus 1. So sine of 2t plus 1, and the derivative of that is going to be 2 cosine of 2t plus 1. So now I can make my substitutions correctly. So this is going to be sine of 2t plus 1. G prime is 2, and I have an extra 2 here, so let me erase that one. 2 cosine of 2t plus 1. And on first look, these do not appear to be the same. Here, I'm saying that dz dt is sine of y times 2t plus 2x times cosine y. But remember that y, and we really should have done this over here. We have three variables floating around in this equation, so we should have replaced y with what it is equal to, and y, remember, is equal to 2t plus 1, and x is equal to t squared. So if I make those substitutions in there, and also cosine of y, again, y is 2t plus 1. So let's replace y with what it is in terms of t. And we now have our final answer, and if you look at these two, notice that we got exactly the same thing. So there are really two ways to do it. One way is to use the chain rule, and then the other way is to do it directly by making some substitutions. Both of these methods are going to have their advantages and disadvantages, so something we need to keep in mind. Well, let's go ahead and take a look at another example here. In this example, we are told that w is equal to x squared times e to the y, x is equal to 4u, and y is equal to 3u squared minus 2v. Let's set up this relationship here. We have more variables now, but the application of the chain rule will occur in exactly the same way. So I have w as my dependent variable. W clearly depends on both x and y, and x depends on u, and y depends on u as well, but it also depends on another variable, v. So if I want to compute something like dw du, then I can, and you know what, actually we can also say that x is a function of v, except that we can actually write in here plus 0v 4u plus 0v is the same thing as just saying 4u. So I'm going to write this relationship here, and we're going to now want to compute dw du. So if we think about what all of these derivatives are, we're going to have the partial of w with respect to x, the partial of w with respect to y, and then we're going to have, again, we're going to use partial operators here because we're going to have x dependent on two variables, u, and then we'll have dx dv. This chain here will be dy du, that's y is connected to u, and dy dv. So we can follow along the chain to compute what we want. So if we want to have dw du, we've got to ask ourselves, well, w depends on x depends on u. So if I follow the chain going this way, going down, and x's dependency on u, and I also do y depends on y, and then y depends on u, this tells me exactly what two products I'm going to need. So the first one will be, we see dw dx times, now we want to have dw du, so we got to cancel out the x's and multiply that by dw du so that what we end up with is dw du. But keep in mind that this is the effect of, this is what we'll call the x effect. Much like in an earlier problem where we looked at corn production as a function of rainfall and temperature, we had a rainfall effect in terms of the partial, and we had a temperature effect. So we can think about this as the change in w with respect to u that is caused by x. Now we're going to add to that also the contribution of dw dy. So how does y affect the change in w? Well, y affects w, but u affects y. And again, we see that those cancel and we get another dw du, and we can think about this as the y effect. Great, so now we need to find these partials, and we can think about what dw dx would be. So I'm going to do that off to the side here. I'm going to write dw dx, so that's the derivative of w with respect to x. And when we look at this guy here, we see that e to the y will factor out, and the derivative of x squared is 2x. So I'll have 2x e to the y. And then we're going to need dx du. So take the derivative of x with respect to u. So x is equal to 4u. The derivative of 4u is 4. Then we're going to need dw dy. And now we can think of x squared as being constant. So the derivative of e to the y with respect to y is just e to the y. And so we still end up with x squared e to the y. Although all these partials can be done in Wolfram Alpha, it doesn't need to be the case that you do them all by hand, but I'm just doing them here just as a way to practice and continue thinking about taking partial derivatives. And then lastly, I need dy du. And so I'm going to look at this guy here, and I need to take the derivative of that guy with respect to u. So v is considered constant, so the derivative of negative 2v is 0. The derivative of 3u squared is 6u. And now I can put these together and write that dw du is 2x e to the y times dx du is going to be 4 plus dw dy is x squared e to the y, and dy du is 6u. Just like in the previous problem, we have too many variables in this equation. We have x, y, and u. So I want to get everything in terms of u because I want to show the dependency of w onto u. So I'm just going to replace x with what it is equal to. So that's going to be 2 times x is 4u, e to the y is 3u squared minus 2v times 4, plus now I'm going to replace x with 4u, so I'll have 4u squared, e to the y. Y is 3